All right, folks, let's start. This is Dr. Yuzo. This is ECE 341 Power System course. And first of all, can you guys hear me? And also being able to see my shared screen under the dot cam. All right, thank you guys. Thank you for letting me know. And then let's move forward. First of all, we are here. Okay, in the Gantt chart, we are here. Okay, so the first lecture for the new module 3, and by the end of which we're gonna have midterm 1. Okay, we're gonna have midterm 1 by the end of this module. So today is the first module for first lecture for module 3, symmetrical components and networks. Okay, and before that, okay, let's talk about what is this. You guys should know this, right? What this problem is. It's quiz 1, okay, quiz 1. So let me present the detailed solution for quiz 1 to see what we should do about this problem. I haven't got a chance to grade, so I don't know how well you guys did. But any questions regarding the quiz 1? I mean, non-knowledge related, like the technical problem. Find where is the quiz 1 and understanding the time and also being able to smoothly upload the handwritten works. Any trouble in those things? Any questions? Any feedback for using Canvas, basically? Anything like those?
I think it was easy enough to do it that way.
All right. Thank you, Noah. Thank you, Noah. Anything else? And I think you guys also like the time, right? It's 24 hours. So as long as you are able to squeeze out 1 or 2 hours, you should have no issue of time. So that you're able to perform as the best as you could, basically. That's my point. So this is obviously the best performance you can have, right? So should be a good news to you guys too. All right, so if everything like these are fine, then let's move on to see the solution here. Okay, this is single phase circuit, and obviously first thing we need to do is, let me use the black color. The first thing we need to do is, how about consider this branch and this branch respectively as 2 total impedance, say Z branch 1 and Z branch 3. How about that? Since I'm thinking this is branch 2. But if you do that, then this basically gonna end up with the impedance. I'm just using a rectangle to represent. Okay, so it's not resistor, it's not inductor, not capacitor. Not necessarily. So I'm just using a rectangle to represent a impedance. And you have ZB3 here, ZB1 here, right? This is 100 ohm source over here. So the point is what? The point is how these 3 impedances connected together, right? That's the key. You need to correctly identify the circuit before anything else. Otherwise, nothing gonna be right. Okay? Otherwise, nothing gonna be right. Does it make sense? So in this circuit, it's actually, as long as you calm down, you can tell actually what connection this is. ZB1 parallel with 100, and then what? Series connected with ZB3, right? This is the correct connection in your mind, okay? Before anything else. Because if you have a wrong connection understanding of the circuit, then, well, it couldn't be right. It couldn't be right. The answer couldn't be right. So if this is clear, then the ZB1 equals what? Just 100 as real part plus what? J omega L as the imaginary part, right? J omega L is this guy. So you substitute, and also this guy is equals to what? 2 pi f. But be careful, the problem is telling you the f is not 60, but it's 50, right? So the answer is 100 plus 80J. Similarly, GB3 equals to 150 plus J omega, another inductor. And then you end up with 150 plus 82.76J, right? Two impedance into the circuit. And the rest thing is actually fairly easy. And the first question is what? First question, let me see. The first question here. First question asking for total impedance, apparent power. Total power, well, C total, as we said, it's just ZB1 parallel with 100, series with ZB3, right? And after some algebra, you end up with basically around this number, right? Total impedance. What does it mean by total impedance? Total impedance, basically, the equivalent circuit is just a one source feeding one single total impedance, right? So then the total power is very easy. You have a voltage right across it, and total impedance, and then which formula you want to use? Magnitude voltage squared divided by what? The total impedance conjugate. Does it make sense? And then what is in the numerator? 30K squared. Magnitude means magnitude. You can't involve the 60-degree in here, right? You can't involve it. 30K is the magnitude, and you're using it only, right? Impedance, then just 229.8 negative 25.8 degree, right? And then what you got is 3.53 plus J 1.5 mega VA. But this is a P total. This is Q total. Right. This is the question A. Any questions regarding question A? Any question, any concern? Or you can also ask, well, the roadblock you ever had in your solution, even though you're...
Part A, don't they also need the power factor? Or...
Say that again?
For part A, did they also need the power factor, or did I miss that explanation somewhere?
Let me see. Yep. Gavin is right. He's also asking for the power factor. No, that's right. So we go to the power factor. A power factor is what? A power factor is very simple, right? I mean, you have active power and apparent power. The easiest way is just to use them, right? Just to use them. Active power divided by apparent power magnitude, right? And that was 0.9. Of course, if you lose the parentheses, you're going to lose a little bit point. Okay, so this is lagging or leading. You don't even need to go to the impedance angle. You don't even need to go to the voltage or current phase angle to check.
Lagging.
That's absolutely lagging. Why is lagging?
Because we only have inductors.
Exactly. Noise, exactly right. Look at the circuit. You don't even have a capacitor. How could it be leading? That's impossible. That's absolutely doesn't make any sense. Or if you check out our notes You're gonna come up with the same conclusion based on what? The positive reactive power, right? So this is something definitely lagging. Okay, it's definitely lagging. All right. And this will be a question. Any questions? Any other questions? All right, if this is fine, then we can move on to question 2, which I have to check. Okay.
Lagging is always, whenever we do the inverse cosine, if we know it's lagging, it's positive angle, right? It's not negative angle.
Angle is a positive angle. Lagging is positive angle, correct?
Okay.
Yeah. It's definitely, if you're looking for that angle, yes, it has to be positive. Because if you do inverse cosine of this guy, definitely going to give you the angle value. However, it doesn't give you the sine. The sine is up to the your extra analysis. Okay.
Whereas tangent, if we use the tan of the real and over imaginary power, that's going to give us the correct sign no matter what, right?
Yes, yes, that's true. However, what I'm saying is, if you given power factor without giving any active or reactive power, then how you find the theta sine? You need to have an extra analysis. Okay, but tangent, yes, the tangent can tell, because your positive q and negative q give you different angle sign. That's true. With inverse tangent, you can tell. Okay. All right. This is the question A. Question B is asking for active and reactive power of R3. But be very careful. Okay. It's asking the active and reactive power of R3. And so guess what? This circuit does not work, right? Why is that? Because this circuit doesn't even have R3. Right? R3 is hidden inside of here. Of course, you don't want to use this circuit anymore. This circuit now just help you to better understand the connection. Okay, you don't want to use this circuit to find R3 because here you can only see ZB3, not R3. Right? So R3 is here. This guy. So how to find the power of this guy? The easiest way is you have impedance of R3. And then what else you can have? Find a voltage of it? Well, maybe. But how about current of it? It's much easier, isn't it? You have the current of R3, and you have impedance R3, and then you apply the one of the versions of the single power formula. It can do the job, right? Now, how to find the current through this guy? Obviously, you need to find the current through this guy rather than the current anywhere else, right? So what is the current through this R3? What is it? Nothing but what? Source current, right? Nothing but source current. Right? R3 just the current, it just equals the source current. And it equals to what? How about just the source voltage divided by the total impedance? And then you substitute everything in. And then be careful, the unit is the kiloampere. It's kiloampere. So this is the current through the R3. And also, as I said, is also the source current. So this current, we go ahead. Okay, looking for this guy, right? The power of the R3. And then what do we do? The formula is the current magnitude squared times the impedance. Right? And if you do this, then 0.13k squared times 150. Well, without doing anything, of course, you're expecting to see what? 0 reactive power, right? Does it make sense? Because we're looking for a power of a resistor. Excuse me, Zach, you need to mute. All right, so here we got what? Basically 2.5 megawatt as the answer. And no reactive power, because this R3 is purely a resistor, purely resistive load. Zach, are you there? You need to mute. Right. So this is the answer for question B. Any questions? Any questions?
I guess I have a question regarding like reactive power in general. I'm just kind
In
of
general, yeah.
I'm
Just
just kind
have
of
a general
wondering,
question. Yeah, what is it?
why is this so bad that we have, I guess, the reactive power? I mean, like, if it's not like you're losing the power, you know, why is it because of the inherent phase shift that it's going to cause on signal? Is that why the power?
Repeat your question again. Why we hate reactive power, you're saying?
Is it because of like the shift that can be
No,
associated?
no, no. I'm asking you to repeat your question.
Like, why is reactive power? Why is it really bad for?
No, no, no. First of all, let me once again remind Zach, you need to mute. Let me type this. And then go back to the John's question. So reactive power a lot of times is necessary. Okay, you have to have the reactive power there, otherwise the system won't work. Okay, so don't take it wrong. Reactive power is necessary. The reactive power is inevitable. Without reactive power, you won't be able to do a lot of things. Okay, so keep this in your mind. It is necessary. We need it. And however, we also need to correct it. Okay, we also need to correct it to improve the power quality by conducting the power factor correction. Okay.
I mean, I guess I'm just kind of wondering, like, why is this power factor? You know, if you're not like burning extra power, why exactly is it necessary to improve the power factor? Like, I mean,
First of all, reactive power is introducing harmonics. This is the one thing. The second, reactive power could introduce the face off between the voltage and the current. And why it is bad? Well, providing certain amount of total apparent power, if your active power percentage is high, that means the useful power is high. If the reactive power percentage is high, that means the useless power is high. So,
so basically, the biggest reason is because reactive power has inherent harmonics that we don't like introduced to our system.
This is part of the reason. Two reasons. One is it's introducing the reactive harmonics. Okay, it's absolutely true. And the second is it is not useful as active power. Active power is the one that's really doing the job.
Okay, but I mean, okay, I guess I see where the harmonics could be part of an issue, and
yeah,
I mean,
because they try to find the power factor. I think I present the complete version of a power factor definition, including the harmonics and also including the phase difference. Okay, it's power factor equals to what? Anyone remember when I?
It can be cos theta v minus theta I. It can also be the total power consumed, real power, over the magnitude of complex and real power.
Yes, it's always equals to active over this. No problem. However, is equals to what? Further equals to what?
Cosine theta v minus theta I.
This is part of it. What else? The current RMS fundamental divided by total current RMS. This is what? Fundamental over the total RMS. This is the harmonics part. How harmonics play a role in the power factor. This is the face-off. The product between two. Okay.
And so that harmonic is because of those two magnitudes in specific, right? We're multiplying the real and the imaginary magnitude and then multiplying it by the power factor. That's the prime issue, right?
The prime issue of what?
I guess I get what you said.
Low power factor. Yes.
Yeah. Okay. Because I guess where I was coming from is like, if you didn't really care about reactive, or why even add a cap or a capacitor, so you'd save on hardware if it didn't really matter. But
well, I guess it really matters. Your power quality is up to the power factor. How much useful power is there? Of course, it matters. It matters. You're wasting a lot of time. No, not time. You're wasting a lot of power.
Okay.
But don't confuse it with the efficiency. Okay, efficiency is not the same concept. That's the output power over the source input power. That's different concept. P over P. This is over S in terms of magnitude. Don't confuse with the efficiency. There's a difference between those two. Right? All right, let's continue our quiz 3 by question C. Question C is applying capacitor across the source. Okay, across the source. Across the source, then, so the new power factor is required to be what? 0.95. From here, we got the new power angle. So it is told to be what? Leading, right? It's asking for leading one. Yeah, leading power factor. So this angle is negative. We want to build a power triangle like this with the what? Exactly same active power, which is 3.53 megawatts, right? Exactly same active power. Active power you can't do anything about because you're adding capacitor only, right? And this angle is theta prime, from which you can tell what is the new reactive power, right? From this triangle, which ended with 1.6 mega, of course, J VAR, right? In your mind, you're very clear this guy is equal to what? Is the result of original total reactive power plus the additional the added capacitor reactive power, right? This is the very logical equation. So the new reactive power this guy, is the result of adding extra capacitor. So original reactive power plus the added reactive power equals to the reactive power for now, right? So this guy equals what? This guy is nothing but here, right? Nothing but this guy. So from here, you can tell what is the QC. This is the very simple math. And then QC just equals to negative J 2.86 mega VAR, right? So now you know the added capacitor reactive power. Then you're looking for the corresponding capacitance value. Well, this guy is equals to what? It's the V source voltage magnitude squared divided by the capacitor impedance conjugate, right? This is how we find out the capacitor power, capacitor apparent power. Of course, this is a reactive power, but it only has reactive power. It equals nothing but this, right? Apparent power. So from here, you can find the actually impedance of capacitor equals to negative J times 314.69 ohm. Right? And from here, you further find the capacitance is about 10 micro. 10 micro. Take a look to see any questions. Yep, you add a about 10 microfarad right across the source. You end up with this required leading power factor. So, any questions? Any questions regarding this? Anything? How many of you got the correct answer for this capacitance value? Good. I saw several names. If you got the correct answer, then that's good. That's good. Okay. Then I think the only difference between this one and the real exam, I think, is of course the circuit is different, and the values numbers are different. However, the major difference would be what the time length, right? That in the exam you need to take much less time to do it. So yep. So yeah, should be fine. Okay, should be fine. Then if this is good, then let's move on to the module 3. Module 3, first lecture. Symmetrical components and the network. Let's see what this is talking about.
Are we going to go over problem 2 on the quiz?
Oh, thank you, Gavin. Okay, this is Gavin's second time remind me missing something. I really appreciate that and apologize for the. Yeah, let's see the problem 2. I should do that, obviously. Thank you, Gavin. So problem 2, what is it? I forgot to do this. Anyways, circuit here, right? So balance the load as this. Right? So the given is what? So first of all, you gotta be very clear what are given, right? VAB 345, angle of 45 degree RMS, nice. So you need to be very clear what are given, right? So first of all, this load is very clear. This is just a balanced three-phase load, delta connected. And this is what? V what? Line voltage of the delta. Since this is delta load, it also equals to what? V phase voltage of the delta, right? So question A is asking, what is the line voltage of delta? Okay. Here. Question B, what is the phase voltage of the delta load? Okay. Same answer. Right? Does it make sense? I mean, this is nothing but a definition of the phase and the line voltage of the delta load. And then C, find the line current of the delta load. Line current of the delta load. Where is it in the circuit? Here. Here. It's here. And the phase current of the delta load is here. Line delta, phase delta, right? So if you come down, you will see actually phase current of the delta is much easier to find. It's just simply because of the Ohm's law, isn't it? And line, and then go back to line current of the delta is equal to a phase current of delta times square root of 3 negative 30 degree. Done. 1 Ohm's law. And 1 phasor calculation. So the phase current here is supposed to be in with 15.43, angle of 71.57 degree ampere. Right? And then times onto this, and with 26.62, angle of 41.57 degree. Done. This problem maybe takes you like, what, 5 minutes? If you have very clear concepts. Okay. Any questions on this problem 2? Any questions? Any concerns? It's again, this is three-phase thing is nothing but you understand the concepts of phase, line, voltage, and the current. Okay. Any questions? Yeah, Neil said, I thought it was super hard. Well, I think I remember I told you guys is that the time given is 24 hours. However, it is not 24 hours load. It's just 1 hour or even less than 1 hour. So it is not easy, actually, quiz, if you do it in class, okay? Because in the past, I used the same quiz at least last year, and the performance was is basically miserable. Okay, but if you given 24 hours to do it, that's different story. Yeah, that's obviously a different story. If it's good, then that's good. Okay, and just make it ready, make your skills understanding ready for the exam. Okay, exam. Any other questions? All right, we can move on to here. Suba is asking, would you be able to upload PowerPoint like we did in 318? What does that mean? What PowerPoint this is talking about? Can you speak?
Like the PowerPoint we had in 318 for the lectures, like the summary.
Summary of
Lectures.
Of what?
Of the lectures.
Of the lectures. Oh.
Yeah.
If you ask the senior students, actually in 318, I do have lecture slides, and I of course upload the slides as well. However, in 341 and the 360, I do not have any lecture slides. Since 2012, I joined SVSU. I've been always using the board to writing notes. And it is preferred way from students, actually. The students gave me the confidence to keep doing so rather than the otherwise. So PowerPoint slides for the lecture? No, I don't have any. I just notes. Okay. And of course, if this notes, this way has any defects or anything you don't think is convenient or good, you can let me know. I will figure out something else, maybe supplemental something. All right. But lecture slides, no, I don't have any. That's the point. Okay, these not these two courses, 360 and the 341. No, I don't have. And you'll say negative 100% effect. All right. Let's move on in this module 3. Okay, so symmetrical components and network, and let's see what they're talking about. First of all, let's learn some new concepts. So this means what? First, we need to review a three-phase balanced sequence component. What does that mean? Is this we learned previously positive and a negative sequence, right? Anyone remember the first one here? This is positive or negative? This one, the positive or negative? Anyone remember? But one is positive and the other is negative, as you know, because they have different phase sequence, right? So this one is positive or negative. 50% chance to win, but positive or negative? Positive, okay. Second is negative. Right, good. Okay, Suba is right. Okay, this is the first one is positive. Okay, so phase B is lagging phase A by 120 degrees. Right? And phase C is leading phase A. In negative sequence, the other way around. Okay, just a different phase sequence, and then what we need to do here is we're giving superscript plus and the minus to represent different sequence component. What does it mean by component? Component means three-phase component. A, B, and C. For example, inside of the positive sequence, you have three-phase positive sequence components, A, B, and C, with plus as superscripts. In the negative sequence, you have, I'm sorry, of course, not positive again, right? They're negative, or say minus. So you have three-phase negative sequence components A through B with A through C with negative as the superscript. Okay. Because guess what? Later on, we're gonna mixing them together. Okay, that's why we are trying to differentiate them by different superscripts. Okay, this is called three-phase balanced sequence components. And here, what does it mean by balanced? Same what? Magnitude, what? 120-degree what? Phase shift. This means balanced. So no matter is positive or negative sequence, those three-phase sequence components are always balanced, right? So this is the so-called balanced sequence components. Okay. With this in mind, then we are trying to express this. For example, I'm using as example because the voltage is going to be the same. Voltage is going to be the same. The principle won't be any different. Okay. What does this mean? What does this mean? Positive sequence, phase A component. Does it make sense? And if we know this guy, of course, is equals to itself, then let's try to express what? Express IB plus. IB plus. IB plus means what? Positive sequence, phase B component, right? And if we are using an operator A to express IB plus in terms of IA plus, well, A is an operator equals to what? Equals to a phasor with 1 as magnitude and 120-degree, positive 120-degree as the phase angle. IB plus equals to A times IA plus. Does this make sense? Well, of course not, because this is A squared, right? Sorry, this is A squared. Does it make sense? Does this make sense now? What I'm saying is A squared, first of all, equals what? A squared equals to 240. Does it make sense? 240 times IA plus means what? Rotate IA plus counterclockwise by 240 degree without changing the magnitude, the length. Look at here. Inside of the positive sequence, A rotate by 120 and another 120, which is 240. You reach IB plus, right? So IB plus just equals to nothing but A squared times IA plus. You see, positive sequence, three-phase components. Let's do the same thing to negative sequence. Using the same operator A. The negative sequence, what do we have? IA minus what equals what? IA minus itself. IB minus and IC minus respectively equals what? IA minus and A squared IA minus. Does it make sense? We are trying to do what? We are trying to express all the sequence components in terms of phase A component in the same sequence. And if balanced, what do we have actually? So it's IA plus IAB plus IC plus equals what? When balanced, is the vector, or say the phasor sum, is equals to what? 0, right? If you does it make sense? If you substitute IB plus and IC plus by A square IA plus and A IA plus, and then you end up with this. Same thing here. You can have 1 plus A square IA minus equals 0. Right. Just trying to get used to the names, the labeling, the basic relations. It's actually not difficult at all, right? It's not difficult, not yet per se. Okay. Well, the things is just like this. If we only have balanced positive sequence and negative sequence, again, since they both are balanced, then our power system is very clean. Okay, going to be very, very clean. Very nice. However, there's something unbalanced, right? Have you ever heard of unbalanced, this term? Now, how we introduce the unbalanced? Okay. Did you see? Who is the problem? Who is the problem? Who is making unbalanced happen? Also three-phase, okay. For balanced two sequences, there are three-phase. The unbalanced one remains as a three-phase unbalanced. Unbalanced zero sequence components. Zero sequence means what? Superscript, we're gonna label them with superscript of 0. It is unbalanced. Why it is unbalanced? Listen carefully. You have same magnitude among three phases, but what? Same phase angle. Be very careful, okay? Same magnitude is a good thing. However, same phase is a bad thing among three phases. It is introducing unbalanced. Be very careful. Balanced means 120-degree phase shift among three phases. That's a good thing. Balanced. If they have exactly same phase, that's bad thing among three phases. It is introducing unbalanced. All right, remember this if it doesn't make quite sense yet. Okay, remember this. Okay, because if you're thinking about things, maybe same magnitude, same phase, are very nice, right? No, it's absolutely not. Okay, to three-phase power, it is bad thing. It's introducing unbalanced. Okay. So, who are they? First of all, who are they? IA0, IB0, and IC0. And the relationship, very easy. Identical. They're same. Same vector or same phasor. Therefore, this is unbalanced. Unbalanced. Okay, one more time. Unbalanced. Let's see how it screwed up the total system. Then now it's a total three-phase. Unbalanced. Either voltages or currents, okay, same concepts here. Let's see. Due to positive sequence, negative sequence, and zero sequence, we come up with the total three-phase unbalanced. Okay, they're what? Let's once again use the current as the example. So total current for three-phase, obviously, just IA, IB, and the IC. We have been using quite a bit. Okay. This is not surprising. Total, just IA, IB, IC. They're equals to what? To IA, we have IA zero sequence, IA positive sequence, and a negative sequence. Same thing to IB. Right? So for each phase total voltage or current is sum among three different sequence components. And if you substitute phase B and phase C current in terms of phase A, then what do you got? Phase B zero sequence is equals to what in terms of phase A? A zero, which is mentioned here. And then phase B positive sequence in terms of phase A is what? A square, IA positive, right? Phase B negative sequence component equals to what? A times IA negative. Does it make sense? Similarly, in the phase C, we write everything in terms of phase A as well. So we end up with this. Does it make sense? So we're expressing the total three-phase current in terms of what? Phase A three sequence components. Right? Phase A three sequence components. Right? So make it so it looks easier. In matrix expression, and what do you have? A, IB, IC equals to what? How about a square matrix times IA0, IA plus, and IA minus. And what are the entry here? First of all, what is the dimension of this this matrix here in the middle? What is the dimension? 3 by 3. Yeah, 2 is right. Yeah, 9 is right. It's 3 by 3, right? 3 by 3, up to 9 entries. All right. So there are what? 1, 1, 1, 1, 1, 1, a square, A. Take a look to see if this makes sense. Oh, I'm sorry. This is square. This is A. That's better. Right? So here, this is A square. Here is A square. This is A, this is A. And we are naming this total current three-phase vector as vector capital A, B, C. This is vector name. The vector name, including 3 entries, IA, IB, and IC. It's just equals to one this middle 3x3 matrix. We gave a name as capital A, matrix name. Left times onto what? This is the guy we learned today, most important one. Call it capital A, and then base A as subscript, and 0 plus 1 as a superscript. Okay. And this guy is called current, because we are talking about a current. Then symmetrical components. Okay, components. Right. So this guy is really the title. Call it symmetrical components. Call it symmetrical components. All right. It's not something very difficult, but new. Okay, just a new concept. And of course, we can go the other way around, because this is looking for the total unbalanced three-phase current based on the given, or say known, current symmetrical components, right? Now, if you're looking for the symmetrical components, of course, you can do that too. And then it equals to what? It equals to total current times the matrix A inverse, right? Any questions? Take a look to see any questions. So back and forth, 2 equations, 2 formula, let's say. Okay. Any questions? Because this is not right. Okay, that's why I'm keep asking. This is not right. I hope you can find the what's the mistake here. Okay, anyone know what's the mistake here?
Does A inverse need to be pre-multiplied instead of post-multiplied?
Very good, very good, excellent. Okay, Noah is right. Okay, Noah is right. You cannot do this. Do this. Okay, that's absolutely not legal. Instead, it is left times by the way, these two are absolutely different. Okay, absolutely different. In the matrix operation, you can't reverse the order because it matters. It's not like a algebra. Okay, it's a matrix algebra, or say it's different. But why is that? Why is this not this? Anyone know? Anyone knows why?
I think matrix multiplication, the commutative property does not hold, right?
Specifically, what's that mean?
You can't, just because it's multiplication doesn't mean you can't group them in different locations. They're not the same. They're not exactly the same.
Yep, it's very blur, but basically right. It's
Plus,
basically right.
I mean, you also have the once you do the inverse matrix of A, you're going to have, no inner size. They're not going to be the same dimensions.
Yeah, basically it's same. Is right. The John's answer is right. Okay, and also Anil mentioned the column should be same. This is actually a checking. The column should be same is not the reason, but the result. You can use this term to check if it's right or wrong, because otherwise it doesn't make sense. I understand what you're saying. However, it's not the reason. The reason you need to go back to the matrix algebra. So from here, let's see how to derive the symmetrical component, right? This is our goal. From this equation, how to find derive this guy. How to derive this guy? In algebra, you derive a constant or variable here. What do you do? Divide by a on both sides, right? However, in matrix, you do not have divided by operation. It doesn't exist. Now, how to make this a gone? You need to build up a unity matrix here, identity matrix, instead of constant 1 in algebra. In matrix algebra, you need to build up a identity matrix. How to make that happen? That's left time A by A inverse matrix. Okay. And on the left-hand side of the equation, you gonna do the same thing, left times on this. The right-hand side is left time. On the right-hand side of the equal, you are doing left times. On the left-hand side of the equal, you're gonna do the same thing, left times. Okay, you can't do right times. All right. But because of this, A minus times IABC equals to what? This is what? Identity. Identity, well, generally speaking, is represented by I, capital I, and times IA0 plus minus. And the identity matrix is like a constant 1 in the algebra. You can save it. That's why we come up with this. That's why. It's actually algebra. You're not doing division. You're doing times, and so that you can see an identity matrix. By the way, what does it mean by identity matrix?
Usually, are you talking about the process of getting the inverse using the identity matrix, as in?
No, what is identity matrix?
It's a diagonal matrix with ones.
Now, here we go. Here we go. So, main diagonal ones. 0 elsewhere. I mean, don't take me wrong, okay? This is not a single 0. It's just no matter how many entries, they're all zeros. Okay, they're all zeros. This is identity matrix. Okay. What about it? But you use the identity matrix times on any matrix, they end up with same matrix. It's just like the feature of constant 1 in the general algebra. This is how we end up with this. Okay, so once again, these two equations, two formula is going back and forth. Given symmetrical components, you're looking for the total unbalanced three-phase current, or the other way around. Given the three-phase unbalanced current, you're looking for the symmetrical component. Well, the significance of the symmetrical components is what? Once you know it, you can easily tell what? Everything, right? Once you know these three guys, you immediately can know what is IB0, IC0, IB plus, IC plus, IC plus and IB plus and IB minus. I'm sorry, this is from IA plus you can know IB plus and IC plus. From IA minus you can know B minus and IC minus, right? So immediately you know everything in this system. You know everything in this system. That's why it's a symmetrical component. Right? Well, this is the concept. But let's still expanding these two metrics into equations. Okay, so still expanding this because a lot of students are much used to the equations. Okay. First of all, if you're looking for the IB and IC, they're equals to say in this way. Symmetrical component this is the one way, right? The other way, for IA0, IA plus, and IA minus, right? So this is knowing the symmetrical components. You're looking for the three-phase balance, unbalanced total current, and this is knowing the three-phase balanced current, looking for the symmetrical component. So be very careful which one we are talking about, So here, you got to be very, very careful. Very, very careful. There's a tricky constant. From matrix expression, you can't see it. However, it does exist. 1/3. Okay, you have a 1/3 as coefficient. Don't miss this. Okay, so these are the formulas where you probably feel more comfortable in the exam problem calculation. Obviously, the second one is given the total three-phase unbalanced current. Looking for the symmetrical components. Take a look to see any questions. Any questions? Any questions?
Why does the a squared kind of flip flop how to describe it. In the top one, it's a squared on the IA plus for IB. But then when you go down to the middle one, when you're in the IA plus row, the a squared is on the IC. Why does it? Is it actually moving, or am I just seeing a pattern that I'm not actually should see?
Well, don't try to remember this pattern. I mean, it's just the formula is just like this. And if you ask me why, let's go back to here, the notes here. For example, let's say, given the symmetrical components, you're looking for the IABC. IA is fine, just a summation of 3 symmetrical components. IB equals to what? IB equals to IB0 plus IB plus and IB minus, right? This makes perfect sense, right? Total, just the equal total of.
Yeah, I get the.
And then you.
IBIC. It was the IA0 equals and the IA plus and the IA minus equals that. I guess threw me for a loop where the a squareds come from.
Yes, it's completely because here. Okay, it's completely because of here. You're substituting the IB plus by a square, IA plus, and then you substitute IC plus by a times IA plus. It's different. Okay, so you're seeing a square here, a square here, a here, and a here. And here, it's the same thing. You do the inverse matrix, and then you still seeing a square here, a square here, a here, and a here. They're kind of but just make sure you copy the correct formula. And if you really conduct the inverse matrix calculation here, you can tell. Why. It's a at there and a square at there. Yeah. All right, I think today we are a little bit early. Finish everything up a little bit early. So, any questions regarding this class? Regarding the quiz? Anything else related? Anything I can provide help with?
Would you maybe be able to show the formula that you used again for the trying to reduce the complex power part on the quiz that you were going over?
Which problem, first of all, you need to tell me?
That would be 1C, applying the capacitor.
Yeah, here we go. What about it?
I was just, I didn't get the same result. I ended up getting like 50 millifarads or something instead of 10 microfarads.
You're saying you end up with the exactly same reactive power here? Are you?
You see, no, I didn't. I guess I didn't.
Then, of course, your C wouldn't be same. Then you need to go back even further. Are you getting the same, the new total reactive power, 1.16?
So how is it that for power factor? Oh wait, I guess did the I guess I'm wondering, why is it negative 18.19 degrees?
Your new power factor is 0.95, and you do inverse cosine, end up with 18.19. And this is leading, so it must be negative.
Oh, it wanted leading. I must not have seen that. Because if it was lagging,
It is the
it-
required leading. You know,
correct.
the original power factor is 0.9 lagging. Now you improve the magnitude of the power factor, but also it becomes leading.
Oh, that's because the question must have said 0.95 leading, correct? Not-
Correct.
Oh,
Correct.
okay.
It did.
That was my mistake. Got it. Okay.
And, as further evidence, where is here? You guys see it?
Yeah.
It's leading.
I'm kind of surprised though that you know, if I thought it was going to be that amount lagging, why was it that I ended up getting a larger capacitance?
I know what you're saying.
You know, because if I needed to shift the phase,
You need the smaller capacitor. You just need to. You need if it's asking for 0.95 lagging, then you need smaller capacitor. You don't need to do that much.
so basically somewhere in the math, mine should be off then as well. Besides for the fact that it, you know, it was.
Of course. You basically you're thinking this way, right? You see the middle as well, unity. This way, let's say the define as lagging. This way is leading. Now as what? Now as like 0.9 lagging, right?
Yeah.
What you need is 0.95 leading. This is required, right?
And that distance
What is
to
required?
change the.
However, if you miss the leading or lagging, you are doing this. So you just go back to this part. You go back by this little. However, it requires to go back to here.
Yeah, which I would have thought I would have, you know, obviously had a value less than, you know, if I did logically, I'm just trying to think if I had a power factor that was lagging in this case of 0.95, shouldn't I had got a value smaller than what the solution was rather than?
Of course, that's exactly what I'm talking about.
Okay, I see.
That's exactly what I'm talking about.
Okay.
Yeah. You make it less inductive, right? Less inductive. You kind of compensate that inductive is too much, make it less inductive. So your power factor magnitude is going to increase. But the remaining as inductive, which is lagging. Does it make sense?
And so if we were always striving for a unity source, what would be the advantage here in having a slightly negative power, reactive power?
In this particular problem? Or in general, what's the benefit
Would
of
there
having
ever be a purpose for setting something slightly more negative than at unity?
No, actually, no. This is just for setting up a problem. No, there's no.
Okay.
As far as except in power generation, system, you're for some reason you just want to generate certain amount of reactive power for certain purpose. Okay. You can control that to generate a certain amount of reactive power.
So would it ever be advantageous to have, like, let's say a negative reactive power if you were going to, say, eventually attach some sort of load and you were assuming you knew what the load would be? Or?
Yeah, sure.
Okay.
Of course. How much power is all up to the load. Load asks for how much current, therefore how much power. It's not the how much power you're giving it based on what? Based on the requirement from the load. Of course. So don't take it around about the reactive power. Okay, reactive power is required, is necessary. Without reactive power, a lot of things wouldn't happen. Okay? It has to have some reactive power. However, you just correct the power factor at the source end. At the source end, you don't want to mess up the source. This course do have a what I'm saying is, if you look at the module here, you guys do have, I believe some of you guys have already done this, but still you guys do have a test run exam to do. Okay, test run exam to do. In this test run exam, I asked a clear question about, do you have any trouble of using the software, MATLAB or Multisim in 318 actually? So the feedback about that question also mattered. Okay. I think yesterday I just sent an email, no, not an email, a Canvas announcement saying the MATLAB solution you can either purchase on your own or just use the on-campus computers. And guess what? The ITS yesterday night informed that they're considering to purchase campus-wide MATLAB license for students to be able to use on their own computer. It's a very exciting news, but they said it takes a while to make that really happen. So I don't know, by the end of this semester, when you guys really need to do MATLAB related work, finally, I know, right? Has been fighting with them for a while, but still, okay, still take some time for that make happen. Okay. It's still a little bit time period before that happened. Okay, so now they're really looking into it. Okay. And I don't know, by the end of this semester, when you guys really need the MATLAB to do some MATLAB related projects or works, if that license is ready for you to use, it should be. It shouldn't take that long. Otherwise, it's ridiculous to announce such good news to us now. So I actually delete that announcement and then in the Canvas. So let's wait. Now, for now, can only wait. Okay. All right. So thank you again, and talk to you guys later. Okay. Don't forget the test run exam. All right. Bye now.